In the last class, we had discussed digital signal processors. Today, we shall see how maybe a digital signal processor as well as general purpose processor can be combined and put into a single silicon real estate, forming what we call system on chips. SOC or system on chip consists of at least two or more complex microelectronic macro components, which have been previously integrated into different single dies in individual form. Complex functionalities that previously required using heterogeneous components and designing a PCB and interconnecting them on a PCB are now being integrated within one single silicon chip. So, having multiple complex entities, hardware entities coming onto a single silicon real estate is what we shall refer to as silicon on chip or system on chip, not silicon on chip, system on chip. The technologies implementing embedded systems evolved from microcontrollers and discrete components to now become fully integrated SOCs. Why? Obviously, advancement in the silicon process technology, which enables us to have more number of gates and effectively a complete system to be designed into one or few integrated devices. These results in space and power reductions as well as better performance. What are the features of these SOCs? Typically, our SOC incorporates a programmable processor, on-chip memory, some additional functional units which are more application specific like digital encryption standard block or MPEG decoder. This we call accelerated functional units. On top of that, there would be peripheral devices. But this is a very typical SOC configurations. Along with it, we may expect other components as well. And often what we get today is called mixed technology designs, where on chip itself you may have analog component, maybe RF component for SOCs designed for communication applications. You may have microelectronic mechanical systems, because when you are using an embedded system and it has to actuate some action, you may have electromechanical systems on the silicon real estate itself, okay? As well as you may have optical input or output. So, a variety of components can now get integrated, and each component in itself is a complex subsystem. So, you can realize that the effort required to design such a kind of an integrated system would be pretty high. Time taken for designing such system is also expected to be high. So, how to overcome this bottleneck or difficulty? We use a principle what is called design reuse. Make use of parts that have been previously designed as well as tested, and also making use of parts, that is, one particular manufacturer may decide to make use of parts designed by somebody else. So, effectively what we have moved into is the hardware as well as software component model. Classical object oriented programming in software propagates this software component model. Now, we are talking about both hardware as well as software component model. And what that ensures? That ensures proven and tested solutions and avoiding redesign and re-verification of real-time hardware and software components which are to be used for a particular application. This is known as intellectual property based design, and what you get is intellectual property codes as the basic components of such a design. In fact, when we are talking about ARM processor and we refer to as ARM core, so ARM core becomes an intellectual property core. And what is essential in that context? That interface of that reusable component has to be known, and known to whom? Known to an application developer who is designing the system on chip. Now, these cores are available in a variety of form for this purpose. We call hard core, firm core or soft core. In a hard core, the designer of a processor provide the design itself in a black box form. In a black box form, in an optimized layout, that means they provide in a form which can actually go onto the silicon itself with the layout of the components being specified. They also provide an encrypted simulation model so that that component can be used with other components in a simulation before you actually manufacture them. The other variant of the core is called firm core, where you really do not provide the design at the layout level, but provide it at the netlist level. That means at the level of connections between the constituent blocks, maybe at the gate level connections. So, what is the advantage? That it can be simulated definitely, because you have got a netlist connection and specification at the component level. It can be also resynthesized with necessary changes. So, the visibility of the design is more compared to that of hard core. The other one is soft core, where you actually specify the design in terms of register transfer logic. That typical hardware description language is used for describing the design. So, here the user is responsible for the complete synthesis, layout, technology mapping and final production of the chip. So, this becomes a software. So, software codes are therefore can be changed to the maximum extent as per the user's requirement. Now, this leads us to the concept of what are called platforms. Embedded applications are built using common architectural blocks and customized application specific components. And common architectural blocks are basically processors, memory, peripherals, bus structures. Now, these common architectures and these supporting technologies, which are intellectual property libraries and tools to use these common architectures, are called platforms. And platform based designs, because using these platforms other systems can be designed. So, platforms are not just the hardware. Okay? So, what we are talking about, a platform consists of IP blocks like embedded CPU, embedded memory, and when it comes in the form of a hardware, you may not know the details of it, but you can also use the layers and the features provided on the platform for developing the application. So, a platform can come with an embedded CPU, embedded memory, real world interfaces, mixed signal blocks and software components. The tools to use all these elements which has been put into the platform. The software components can be device drivers, real-time operating systems and application code. So, you should clearly distinguish between two aspects. One aspect is I can take a core, an intellectual property core in some form, either hard, firm or in a soft form, add on my design and generate my SOC for my application. Now, these basic components also can be packaged in terms of hardware and software elements and can be delivered to a customer for developing his application. Here he is not doing really the silicon compilation of the complete system. He is using the components provided by the manufacturer, which includes both hardware as well as software elements, and then designing the system. And this is what is platform and platform based SOCs. There are different classes of platforms. Full application platform. Platforms that let derivative product designers create complete applications on top of hardware software architectures that I was talking about. So it can come with a set of hardware modules. It may be a complex dual processor architecture with some kind of an hierarchical bus system tailored to a specific product's requirements. And to use that hardware, a layer of firmware and driver softwares are provided. There are various examples. Philips Nexperia, TI's OMAP, they are example of what we call full application platform. So here the application development effectively means developing the software and maybe some add-on hardware on top of the platform that has been provided. Then there are processor-centric platforms. They are typically centered on specific processors, and they provide, along with the processors, the key software services, the real-time OS kernel, which would be supported on that platform. So examples are what we call ARM MicroPack, ST Microelectronics provides ST100. These are all examples of processor-centric platforms. There are at the same time communication-centric platform where the basic objective of the platform to provide the communication fabric optimized for specific applications. We had already seen ARM's AMBA bus. So ARM's AMBA bus as well as maybe an ARM processor integrated onto a single system on chip can provide an example of communication centric platform, so that you exploit that bus to add on additional components, have communication between them depending on the application that you are looking at. Then we can have configurable platforms. Here the programmable logic is added to the platform, which allows consumers to customize using both hardware and software. So you have got fill programmable gate arrays added to hard-coded processor-centric platforms. So when you talked about processor-centric platforms, it was primarily the processor and some additional components with a software services bundled with that processor-centric platform. Now here we have got additional fill programmable gate array logic or any other form of configurable logic. So you can customize in terms of software as well as hardware. There are examples. Altera Excalibur platform with ARM cores, that means with ARM core it provides additional FPGA blocks. Then Xilinx Vertex 2 Pro, which is built around PowerPC. So these are all examples of configurable platforms, and this leads us to a concept of what is called configurable computing or reconfigurable computing. We shall come to that point towards the end of this class. These multiprocessors SOC or MP SOC, they are typically full application platforms. In fact, other way around, majority of your full application platforms are nothing but multiprocessor SOCs. So they have got a CPU and a DSP. These are very minimum and common requirement. Some of the special hardware blocks, the hardware blocks designed from special purpose functions, and there will be mixed signal elements. That means they are for analog interfacing. So you have got analog as well as digital interfacing elements. Customized memory system and lots of software on top of this hardware, so that application developments gets facilitated. So examples, I had already started with this, referred to Philips Nexperia. So here we had talked about Trimedia CPU, okay, Philips, and MIPS processor, which is an example of a RISC processor. These two cores sit together, okay, and you have got other accelerators which are meant for accelerating some special functions, and these are the individual buses and buses to SDRAM and the bridge between the buses of the individual processors. So this is a kind of a multiple processor system, and since Trimedia was primarily designed for media processing like video and image processing tasks, this SOC, that is application platform, was designed by Philips particularly for applications like set-top boxes. TI OMAP has got C55X DSP, we have studied that already, as well as ARM9, these two, okay, and there are variants. This is, we are looking at one particular OMAP, and they are being used together for multimedia as well as, in fact, handheld portable communication terminal applications. This is an example from ST. Now this is very interesting because it targets mobile multimedia, but it's not just two processors, it's a multiprocessor of multiprocessors. So you can see the complexity to which the design can go up when an SOC is being designed for applications. So here the audio accelerator and video accelerators are collection of heterogeneous multiprocessors, and they are actually used along with the ARM9 core to provide you a platform. So please keep in mind, these platforms is what? These kind of hardware blocks along with the software layer to use these blocks efficiently. So now we shall look at one of them, OMAP, Open Multimedia Applications Platform from TI, in more detail to understand the features of applications platform. OMAP application processor, we have already seen, has a dual core architecture, ARM9 as well as C55 DSP, and its design chain includes software IP, that is OMAP supports several real-time OSs to suit different applications. Okay, so you can use that OSs to program these SOC for application development. You also have application and middleware. There are ported applications and middleware like MPEG-4 decoding, audio playback. MPEG-4 is a video decoding, a video standard, and it's being used for video decoding standards and audio playback. So you have got these applications, these are ported onto it, and these applications themselves can be used subsequently. So when we are talking about a platform, therefore hardware, the basic OS, and this OS is built with a kind of a software architecture envisaged for this SOC, because you got to envisage a software architecture for this SOC simply because you are using two processors, and how do you use these two processors, that becomes a critical issue. And when there are more processors, the problem complexity increases, so you need proper software tools to use these processors for your application development. So always these platforms, application oriented platforms, come with hardware as well as a software bundled together. In fact, this is an example I am showing from for the TI OMAP, and you can see that this is a process by which the features have been integrated from multiple vendors. Okay, so you have got the hardware IP which is coming from ARM, and your software IP which comes from a number of these OS vendors. Okay, you have got Linux, Microsoft. Linux is a public domain which has been mapped onto it. You have got Microsoft, you have got Palm OS, Symbian is the OS targeted for cell applications. So all these are source of software IP, intellectual property, for OMAP. There has been a number of contributors for applications and a middleware, and TI has actually contributed the other hardware IP, the DSP and does the manufacturing, and it has been taken up by a number of device and equipment manufacturers. Okay, so these are some set which is being shown. Okay, and you will find many of these consumer electronics partners as well as cell phone manufacturers have picked up OMAP for developments. So the whole idea here is in the context of embedded systems, you are not looking at hardware or software in isolation, because it's an integrated whole and you are using components supplied by different vendors and providing an environment to an application developer to develop his customized application on top of these platforms. Let's look at OMAP hardware architecture. It consists of two basic components. This is your DSP component and this is your ARM component. This is the memory interface. You can see that the same memory interface is provided to both the processors, and each of these processors have got their own onboard RAM, because I already talked about this single access RAM, dual access RAMs, instruction cache, which is already there within the DSP core. In case of ARM core, in fact ARM9 is a Harvard architecture based processor, so you have got an instruction cache and data cache which is separately, and then it has got its own MMUs, memory management units. So through this they are using, this processor is using the memory interface to access external memory. This is also using this DSP MMU through this memory interface to access external memory. You have got a DMA controller, and DMA controllers provides the direct access. So the other element which provides the direct access to the memory is via DMA controller. It has got a number of these interfaces for peripheral devices. It has timers and watchdog timer. Watchdog timer is important for embedded applications, that's there as well. So this is what you have found, that there are two processor cores. They have their own memory management scheme. They have their own what is typically called private memory, and they also have a mechanism to access global memory. They have got a set of peripherals by which they can interface with external devices. They can individually interface. They can also connect to external devices via shared interfaces. So how does these two processors really coordinate? ARM RISC core is well suited for what is called control code, OS, user interface as well as OS applications. And DSP is best suited for signal processing applications like video, speech processing and audio. But obviously you should note that ARM also has got various instructions which facilitate signal processing as well. But what is being emphasized here is the management of the control code, which is expected to be the primary task for ARM. And what has been found also through benchmarking studies, that this combination, that is of mapping signal processing tasks onto DSP and OS onto ARM, is power efficient, because signal processing task on DSP consumes much less power than on ARM. And in fact, if required, you can even use ARM's signal processing capability. So let's look at an example application scenario. Say video conferencing. So in a video conferencing, you expect to send image as well as audio, and that too at a particular frame rate. Typical expectation is 15 frames per second. So you really do not have a jerky vision, and you have your faces, images at regular intervals. So this imposes a real-time constraint on the processing. So C55X DSP can process in real-time full video conferencing application using only 40% of the available computational capability. And it has been also found through benchmarking studies. And therefore, it has got about 60% of the computational capability available for managing other services concurrently. Now, ARM can handle OS operations while video conferencing on, as well as OS applications. If I am having Windows CE on it, it may support Word, Excel, etc. So, what a user can do is, user can have a video conferencing as well as can use OS applications simultaneously because of availability of 2 processor cores on SoC. And you can consider this as a typical application would be like a palm top or a communicator with a camera, so that with or using the camera you can have a video conferencing or video telephony going on, and at the same time you can use the OS based services. And less power consumption is on the whole, because the DSP power consumption is much less for the signal processing tasks. Now, how this architecture really works? Both processors utilize an instruction cache to minimize external accesses. That is what we have already seen in the architecture diagram, and they both use MMU, memory management unit, for virtual to physical memory translation and task to task memory protection, because their tasks, these processors will have distinct tasks and their tasks need to be protected against violations of access. And what is important is, since each of them use MMU, they minimize or optimize on external memory accesses, and external memory accesses are typically power hungry. So, if I minimize those accesses, then I make the whole system as well power efficient. Now, how does it access external memory? It uses 2 external memory interfaces and 1 internal memory port. External interfaces support synchronous or asynchronous memory. Synchronous memory like say dynamic RAMs, and asynchronous memories which would be flash or static RAM. And actually the program would be resident on static RAM or flash. And there is an internal memory port for on-chip memory access. Your critical OS routines are expected to be loaded on the chip itself, as well as the LCD frame buffer. In fact, if it is targeted for your mobile applications, there would be a requirement of an display panel, and in the display panel the data which is to be display panel are to be stored in a frame buffer, which is again a memory area where you have a mapping from each pixel on the display to a memory location in the frame buffer, and that would be very frequently accessed, because there you actually have updates to be displayed to the user. So, that also forms part of your internal memory. This internal memory allows concurrent access from either processor or DMA unit. So, from peripherals you can have fast transfer of the data onto the memory. A number of peripherals can be interfaced, a number of interfaces are supported. We shall look at some of these interfaces because they are interesting in terms of the target applications. It provides camera and display interfaces, okay, because if I am targeting for this kind of embedded portable terminals, then they will typically have a camera connected to it, and so that camera interface forms a part or an integral component of this SoC. It has got basically 2 camera interfaces, a serial unidirectional what are called compact camera port, as well as 8-bit parallel interface. Also it supports bidirectional display interfaces and has on-chip LCD controller, so that the LCD display can be managed. Now we can realize that additional components have been put onto the chip by the designer, that is TI, keeping in mind the target application. Also, there are several serial interfaces: SPI, MAC PSP, I2C, USB, UART. Now, these interfaces, in fact, MAC BSP we have already seen, and through these various devices can be now connected to OMAP. In fact, if you are thinking in terms of using your OMAP processor, this one, as a core processor in a cell phone for data and voice communication, you will require a modem. So, modem can be interfaced using these serial interfaces. Even you can have an additional codec, like say an audio codec, and which can be connected via serial interface. There are other interfaces as well, but we are not going into them in details. So, what is the software architecture? This becomes a key thing because some manufacturer can design a complex hardware SoC, but if the proper software interface or the software architecture is not defined, then using these SoCs becomes extremely difficult. And that is precisely the reason, the point I was making all through, that platforms essentially mean packaging of both hardware and software together. So, software architecture for OMAP defines an interface scheme that allows the general purpose processor to be the system manager. And this interface scheme is called DSP BIOS bridge. And this DSP BIOS bridge provides communications between GPP tasks and DSP tasks. Okay, and this can be used in a way that you are just using a uniprocessor system. So, the basic objective is of using this DSP BIOS is that externally for an application programmer it would appear that he is just programming onto a single CPU, and internally the DSP BIOS is taking care of mapping subtasks to the DSP. So, high level application developers use a set of dynamic link load libraries and drivers and have the feel that they are using a single processor. An advancement on this architecture, why I am showing this is because you can see the complexity that can be added today onto a single chip with the advancement of process technology. The earlier one we talked about primarily as a processor core, DSP and ARM. Now, we have got multiple engines executing multiple tasks integrated on the same chip, and that is what is OMAP 2. Here we have got ARM 11 based microprocessor, which is advanced version from ARM 9. DSP core focuses on audio codecs, echo cancellation and noise suppression. These are primarily important for carrying out telephonic conversations. There is on top of that a 3D graphics engine, which is again basically a processor to enable sophisticated graphics rendering. Also, there is a video or imaging accelerator that handles streaming MPEG-4 video and megapixel resolution camera. So, this video handling and the camera handling is no longer with the DSP. DSP is concentrating completely on the audio task. Also, there would be a digital baseband processor which implements network communication as a cellular modem handling voice and data. In fact, this is primarily targeted for cellular phones, and what today people are talking about is smartphone, that is a phone which has got all elements of personal entertainment as well. So, in fact, you can understand the 3D graphics engine would enable highly sophisticated MMS service, that is the display service on the phone. Video imaging and accelerator would enable you to use the camera, and the digital baseband processor enables you to use the phone as a voice and data modem. And why DSP core focuses on audio? Because you can consider your even cell phone as an MP3 player. So, you can have MP3 data which can be played. So, that whole task goes to the DSP core. So, the architecture now becomes much more complex. In fact, you have got this ARM11, this is a core processor. If you are talking about multiprocessor, this becomes a core processor. You have got ARM11, you have got C55X, you have got 2D, 3D graphics accelerator, you have got video accelerator. So these four processing elements have been integrated together along with various other features. In fact, there is a keypad GPIO, general purpose IO, to interface a keypad, a camera serial parallel interface, that same parallel serial interface that I had talked about earlier. It has got again a security block, that is, if I want to use some kind of an encryption service, so for that hardware has also been provided. And you have got the UART, and this here we have showing a modem chipset. So this modem chipset can be used through these ports. I was talking about the serial ports through which a modem chipset can be used. So these are the serial interfaces which are provided for chipset, and this interface is provided for the actual playing of the sound. So you can find this to be a pretty complex and elaborate processor. So in fact, what has been done is all the functionalities which are required has been built into a single chip. So all blocks here operate simultaneously. So there is obviously no degradation in quality of any service. Why the degradation would come in? If that service is being shared on a single processor, so depending on the load, there would be time allotment on these different services can vary. A simple example is, if the processor is loaded, then there may be a situation where a decoder, a video decoder, may miss a deadline. That means a frame may not be decoded at a 40 millisecond interval, and you may get some jump while the video is being displayed. But since all these are concurrent elements, there is no degradation in the quality of service, and devices which are connected to these elements remains highly responsive. It is not that you have to wait till this device generates an interrupt and the processor services the interrupt coming from the device. Further, to conserve power, each of these subsystems can be shut down when not used, because all these subsystems may not be really used at the same point in time. And these SOCs is suited for implementation of what are called smartphones, and it's being used by a number of vendors like Nokia and others, and even TI says that they will not supply this chip if it's not being used in a large volume. In fact, it's being a kind of an exclusive agreements with the manufacturers of the devices with the actual semiconductor firm. So this is a kind of a platform which is targeted for smartphones, where you can have communications, telephonic communication, you can even have video phone, you can have a FM radio even implemented over there, you can have an MP3 player, you can have a DVD interface built into it, and also obviously you can have a camera and multi-megapixel camera to take snaps. So it's a kind of a personal entertainment station which can be built around entertainment as well as communication station, which can be built around this SOC. In fact, another example towards this direction is digital media processor, which are called portable digital media processors, for providing all these services in a standalone mode. So what we say that you have a device, a chip, which can support video as well as image capture, audio capture, video playback, printing interfaces. So it's just not a camera. Just think that if you have such a SOC, you can get devices which will not be just a camera, but it can be a audio recorder, MP3 player, as well as through which you can print images and everything put together. And in fact, this kind of commercial interest actually drives these manufacturers to design, to visualize and design this kind of multi-processor application platforms. They have provided the platform, and others would be building systems around it. So here it's an example of what I have stated is the functionalities required, and several modes would operate concurrently. And taking this into account, there is a DM310 media processor, which is again an SOC, a multiprocessor SOC, and it has got 4 subsystems: imaging and video, DSP, a set of coprocessors, as well as ARM core. And you will find that ARM core is being used in a very extensive fashion. So you have this imaging and video system has got a CCD controller. I hope you remember that we had talked about CCD as a basic imaging sensor. Now the CCD controller, it's just not a, if you compare this with that of your OMAP interface with the device, OMAP was providing a simple a serial or a parallel data interface. Here you are talking about a CCD controller, that means you can actually control the sensor itself. So that sensor control logic now goes into the SOC. In the case of OMAP, what is expected that your camera is providing the data and you have got the interface to get the data. Here how to extract the data from the CCD sensor itself and how to manage the CCD sensor, that hardware becomes part of the SOC. So it has got 54X, and the other interesting part is, along with these, it has got coprocessors. Coprocessors is an assembly engine. You all understand and by now know that why assembly engines are important for this kind of media processing applications. A spatial engine for doing quantization. Why? Because for compression tasks, quantization is a very important step, as well as variable length coder. A very common example of variable length coder is your Huffman coder, which generates the codes which are of variable length. So you have a targeted coprocessor for this purpose. That means these are all dedicated hardware for these tasks. And on top of that, you have got an ARM core which is managing your system level tasks, just like your OMAP. So the architecture looks something like this. You have got your DSP core, you have got your ARM core, and the DSP core makes use of these coprocessors. And this is your image buffer. So to this image buffer, which is onboard memory, okay, which is also being used by the DSP as well as this coprocessors, which is imaging accelerator, variable length coder, quantization and inverse quantization blocks, and they manage it. And this is the basic SDRAM for other purposes. And this is a separate coder which is primarily looking at the video application. Okay. Now here you will find that the whole approach has been to provide a kind of a digital media processing capability, and you can understand the difference between the slight difference between the representation with regard to the OMAP. What is the basic difference? The basic difference is OMAP is targeted for communication as well as this kind of media processing applications. It is more targeted towards media processing. So you have got actually a CCD controller kind of blocks incorporated into SOC and coprocessors for each and every tasks related to media processing. And we can see now how a complete embedded system can be built around it. So a simple example is still camera engine. It's not just the still camera can be built around it. The still camera can have all sorts of other functionalities related to that. But this is just an example to illustrate how this single SOC can be used to build a complete system, a complete appliance. So here you have got the CCD sensor, analog front-end timing generators and horizontal drive, and that gets interfaced through your CCD controller which is sitting on the chip itself. You can have an additional microcontroller which may be optional. You have a power management circuit. These are basically your memory. Okay, these flash are where the programs should be stored. You have got a speaker output, microphone voice input, secure digital card. You can also ensure a kind of a secured access, color LCD panel, okay, which would be interface to see what is the image being captured. So you can have a image capture. You can even annotate an image with your speech. You can say that I am taking this image on such and such date at such and such place. Okay. So You can therefore find that using this SOC, you have built a complete appliance. Okay, and this is what is a typical example of an embedded system built around, a complete embedded system built around this SOC. Next, we shall look at reconfigurable platforms. What are reconfigurable platforms? Reconfigurable SOCs typically consist of processor, memory, as well as on-chip reconfigurable hardware parts for customization to application. These could be fine-grained or coarse-grained. When it's a fine-grained, you have got FPGAs. The extreme end of the coarse grain, there can be a network of processor, a multiple processors, and these processors can be configured, okay, for your work. And what we say that it's a movement towards application specific programmable products. If I look at ASIC, which is an application specific integrated circuit, there the whole design is targeted for an application. And there the focus is not reprogrammability of that chip. Here we are talking about an application, no doubt, but at the same time keeping in mind the reprogrammability. Okay, so that means depending on maybe change in the protocols, it should be possible for me to use the same hardware and reprogram it and make the appliance. I need not freshly design an ASIC. So what is really reconfigurable computing? So what we say that compute by building a circuit rather than executing instructions. Take for example a simple multiplication here, okay. I am multiplying the two elements by constants a and b, and I am trying to compute the result. Now what is interesting here is, this is a set of assembly language instructions, so it is a multiply load, you can understand this, will be used for computing this function. So if I have the ability to generate a circuit corresponding to this statement, then what I am really doing is a reconfigurable computing. And how to generate this circuit? Obviously I can know the operations. How to implement the circuit? If I have got an FPGA block, I can program the FPGA block to realize this particular function. What is the advantage of this? We need not have an instruction fetch, no instruction cache required, because that is going into the hardware itself. Bus width and constants are typical issues, because in many cases I really do not need 32-bit bus transfers, because say if in this example if x and y are 8 bits and I have a 0.25 and b 0.5, I can have a very simple circuit. So what I have got here is this multiplication and addition at this 0.5 and 0.25 is division by 4 and division by 2 is nothing but shift operations, and I need to do addition. So I've got a very simple circuit, and what I say is that the delay from 2 shift operations and 1 additions all on 32 bits, this happens when we are using the instructions, translating that operation into a set of instructions to this kind of a circuit. So what we have got to 1-bit addition, and shifts are almost free in hardware, because if I am using a barrel shifter kind of a circuit, I am building small such circuits using FPGA blocks, then I can do shift in almost no time. So what we have got now, what are called FPGA based RC, that is programmable fabric that can be dynamically reconfigured, and you have to map therefore this code to FPGA, reconfigure the FPGA, and then do the computation. So you have got a programmability not in just software but as well in hardware. So the typical structure is that I have got a configurable logic, I have got microcontroller as well as the memory, okay, and this logic you can use for programming the hardware. A simple example is this Trisent A7 SoC, which is again using your ARM7 that we had already studied, and this is your configuration system logic block. And these are units which perform basic combinational and sequential logic functions. So a collection of gates, they can be configured to realize different functions, and I can use a set of such gates to realize these functions together. So I have got simple computations, repetitive computations mapped onto now dedicated hardware. And these hardware can be designed depending on the application that you are looking at. And in fact, there is this signal interface so that can be changed from one application to another application. This is an example of this kind of programmable platform that I was talking about, Xilinx Vertex 2 Pro. It has got 4 PowerPC processor cores, okay, sitting on the same SoC along with the FPGA logic to add on the hardware, and it has got serial transceivers to transfer the data. Okay. Then we can have coarse grained reconfigurability. We have got simple logic gates, putting together logic gates to realize simple logic functions. From there you can have a set of ALUs, and you can now configure these ALUs and a set of registers to do some tasks. So it becomes an example of a coarse grained reconfigurability. So potentially an instruction level parallelism of more than 100 you can get, because if you remember, VLIW have got multiple processing units. Now since you have got so many ALUs and registers which you can configure and network, then you can actually have maybe at the order of 100 ALUs, 100 parallel operations being implemented. This is an example of extreme processing platform. I have just shown the extreme processing platform part. This would be interfaced with again a microcontroller core by a semiconductor designer. So what it has got an array of ALUs. These are all ALUs, an array of ALUs. Each ALU has got its own RAM, okay, and it has got a set of IO elements, and you have got a configuration manager where you actually put in the code to say how these ALUs will be configured for a particular computation task, and the data for those ALUs will be in this RAM. Okay, so you can see the extent of reconfigurability that you have got now, and you are using a processor core and you are reconfiguring the hardware depending on the application. The other end is also configurable processors. The previous examples, what we said, we have a processor as well as FPGA. We can now configure these FPGAs or these ALUs depending on the application. Here we are looking at configurable processors. So processors themselves can be configured before you actually go into a design. So processor parameters, registers, etc. can be configured. So what you have, you start with an HDL model of processor and you have got a software development environments, and this is what I call application specific instruction processors, or ASIP. So programmability allows changes to implementation using several different products and high data path utilization. So that means you are configuring, you have the ability to configure the architecture of a processor depending on the applications, not the major part, but at least the registers, the cache size and those elements. But the key problem in this case remains how will your software tool behave? Will you design a software tool for each and every variant of the processor that you are producing? So you have a concept of what is called retargetable compilation. So that retargetable compilation takes as input the architectural model as well as the language specification, and that is used in the code generation block to generate the code for the processor that you are trying to synthesize. Okay. So you can see here I tried to show how this configurability has implication in terms of software technology as well. So what we have today looked at is SoCs. Of these SoCs, we have reviewed OMAP in some detail and got an introduction to the concept of reconfigurable computing. And these, what we have discussed today, is basically a reflection of the current trend of embedded system hardware.